Welcome to our emergency response presentation. We would like to welcome all student teams, subject matter experts and mentors, NASA professionals, TSGC representatives, educators, and invited guests.
Who we are. We are a group of aspiring high school juniors and seniors from around the country who have come together to create a local solution to a global problem: the detection of floods under cloudy conditions as storms become increasingly severe from climate change. Hello, my name is Aryan Paul, and I'm an upcoming senior at Coppell High School in Coppell, Texas, and I hope to become a data scientist.
Hey there, I'm Rachel, and I'm an upcoming senior at Newport High School doing Running Start at Bellevue College. In the future, I hope to be a philanthropist and computer scientist.
My name is Leon Nguyen, and I'm an upcoming senior at Langham Creek High School in Houston, Texas, and I hope to become an environmental engineer in the future.
Hi, my name is Cheryl Sue, and I'm a rising junior at Valley Christian High School in San Jose, California. In the future, I aspire to become a software entrepreneur.
Hello, my name is Esteban Garrett, and I'm a rising junior at Cedar Hill Collegiate High School, and I want to pursue a career in computer science.
In the 21st century, we stand witness to the shift in climate change causes from more natural to more human causes. Our current lifestyle, the imbalance of greenhouse gases in the air, fossil fuel consumption, pollution, and more. As a result, we now see a dangerous rise in sea level as oceans warm up and expand and land ice sheets melt, an increase in storm severity as more water vapor accumulates into larger cloud formations, and as warmer seas create stronger winds and storms.
With an increase in larger natural disasters and phenomenon comes a greater need for satellite imagery and technological advances. New satellites like Sentinel-2, Landsat-8, and Grace Follow-On have provided invaluable data into tracking the effects of climate change and the evaluation of natural disaster damages into the 21st century.
Yeah, unfortunately, the growing use of the internet as a common source of communication and information has spread the dangers of climate change across the globe and has given people like ourselves the chance to embark on local solutions to the global change, whether that be coding analytical programs or a blog on climate change.
With these changes in mind, the goal of our project is to create a web app that can accurately analyze and detect floods, regardless of cloud cover, as well as help warn people of potential water levels as well as flood areas in order to help emergency response. Some of our technical goals are to allow users to input location where we'll analyze potential flooding, as well as to use data from multiple satellite datasets such as the Landsat 8 and Sentinel-2.
Our approach. So in a general format, the steps we took were: we first explored Google Earth Engine, we then explored image visualization within Google Earth Engine, and then we created our algorithm to help us detect floods, and finally we experimented with user interfaces to agglomerate our data and code all into a web app. In our first step, we explored Google Earth Engine and began looking for images to test and analyze from various datasets. Then we began brainstorming different methods and functions for viewing cloudy floods and what variables we would universally use.
Here are a few of the floods we tested on. We tested a flood in Caria do Várzea, Brazil. These floods affected more than 700,000 people in the surrounding areas in the state of Amazonas. This is because of the lack and flaw in infrastructure, like they were using wooden bungalows and dams. So with these lack of infrastructures, it made it easier for the floods to wreak havoc. And because of the lack of sanitation in the area already present, it made it easy for waterborne illnesses to spread. We also got information on a flood in Cedar River, Iowa. This flood, unlike the one in Brazil, was less of a humanitarian issue and more of an economical one. This flood caused over $22 million in damages and 10,000 residents were forced to evacuate. Around 500 buildings and homes were damaged in the floods, and this led to future issues and problems in the community. We also worked on a flood in Kerala, India. About 483 people died in the floods. This is considered a level 3 calamity, and it was the worst rainfall that they had in the region for 87 years. As many as 39 dams were opened, which contributed to the floods, and about 1/6 of the population of Kerala, India was affected by these floods. In our step 2, we started on image visualization. we wanted to display an image of a flood whenever and wherever appropriate that is easy for the user to analyze with the built-in Google Earth Engine functions like geometry, filter, and bound. Furthermore, we had to decide which band combinations was best to display our images. With the use of satellite imagery, we can use bands that are not visible to the human eye to highlight certain aspects of images that we want. After a while, I came across a set of bands that I nicknamed the Golden Bands. The Golden Bands are a set of bands that seem to work well for the purposes of our project. The land contrasts well with the urban area and clouds, and the water, so you can see everything in more detail. The sediment inside the water, which is a sign of flooding, pops out very well as well. This is unlike what I saw in the next one that you'll see, which is called Bright Green. Bright Green contrasted well with the water, but the sediment wasn't as well picked up, and the urban areas and other things on the land itself were not very easy to identify. The next one, which I nicknamed Grape Juice, it's just not good at all. The water and the land seems to just kind of flow together, so you can't really tell which is which, and especially when you get to areas with smaller water, like thin creeks and rivers. The next one we did was a standard false color image, which is good, and it shows that the Golden Bands is just a slight modification to the standard false color image, because the standard false color image contrasts really well with the water and picks up the sediment really well, but I think it could have been better with the urban areas. It took me a while to figure that out, but eventually I got it. And the last one was a true color image, which it's fine, but it obviously could have been better. That's why we're trying to find different band combinations.
So after experimenting with different band combinations for image visualization, we started working on our algorithms. And one of the algorithms I worked on was predicting susceptible areas to flooding. So originally, Ms. Howard built an elevation threshold algorithm with a sample flood from Cedar River, which generated the potential flood area within the radius of the center of the image based on SRTM elevation data, as well as a Landsat 8 image for reference. And expanding off of the program, we wanted to make this function applicable for all areas. So we specified parameters that would allow custom user input on the location and date of the generated image. We also noticed that sometimes no Landsat 8 image would be available for the area and date inputted, so we integrated image collections from the Landsat 7 and Sentinel-2 satellites and added new visualization parameters based on some of the bands Estevan experimented with. This gave the algorithm a larger resource to function on. And finally, this algorithm now includes a slider allowing you to specify how tall you expect a flood to rise. And in response to this, the map will generate new areas in red that are susceptible to potential flooding. This is done by using Reducer to find the average elevation of the SRTM data on the image. SRTM was a very important part of our data set. And updating the image mask with a new number added to the average elevation every time the slider moves.
I independently developed an algorithm which was designed to identify water covered by clouds. In essence, this algorithm uses flood fill and compares the elevation data of adjacent squares in order to identify water. To begin with, this algorithm takes in a region. We then use a classifier to identify water in the Landsat 8 image of this region. Using the coordinates of the region, we break it up into a grid of tiny squares, which we'll basically treat as pixels. For each of these squares, we run a reducer on the elevation data set to find the elevation of that square. We also run a median reducer on the classification image to identify it as water or not. Finally, we run a reducer on the original image to get the RGB values. Now, we can run a flood fill on this grid. Flood fill is a standard O of n computer science algorithm. We first create a queue and add all of the squares which we identified as water to the queue. Now, while the queue isn't empty, we remove the first element from the queue. We then compare it to the left, right, top, and bottom neighbors. If any given neighbor has lower elevation than the current square, then that neighbor must have water as well. Thus, we mark the neighbor as having water and add it to the end of the queue. However, if the neighbor has already been identified as having water, we don't add it again, or else we'll just have an infinite loop. We continue doing this until the queue is empty. Now, we create a new image using the Python imaging library. We transfer the RGB values we got from the reducer into the Python imaging library image. We then overwrite the RGB values for pixels that are water and set them to being blue. The motivation behind this algorithm was that using an elevation threshold to identify water has a flaw, and that is that it could identify an area of low elevation as having water, but that area may not necessarily be connected to a water source. This flood fill ensures that all additional water pixels we identify are actually connected to a water source. However, this algorithm had a flaw, and that was that the flood fill needed to be performed on the local client side. This meant that all of the elevation, RGB values, and water flow classification data needed to be transferred from Google Earth Engine to the local client. This meant that all the data had to be unpacked from the Google Earth Engine data types and then transferred to the client. For large images, this unfortunately takes a very long time, multiple hours, so it was deemed to be infeasible.
Add to the overall program, I created an algorithm to display elevation data in a clear image to add additional information for evaluating a flood's potential extent. I used an SRTM digital elevation image and incorporated GEE hillshade and slope functions while also playing around with gamma and opacity to add texture to the landforms. Additionally, I added a layer to show up parts of the land and water which might be below a user-inputted elevation for predicting where a flood might have an impact.
Finally, we experimented with user interfaces to allow a broader use of our program, giving users with more features like text boxes, checkboxes, sliders, and labels. And with each component completed, we combined our individual functions and components into one coherent program. After reordering our code to make sure our functions did not work against each other, we displayed it into a web app hosted by Google Cloud. To make our web app even more accessible, we embedded it into our own website, which we are currently updating with even more information on our experience at the SEEDS program. You can visit it at detectflood.weebly.com.
Although we are pretty proud of our functioning web app, there are definitely quite a few limitations. For example, we are unable to mask out clouds in our web app. However, we have come up with a partial solution in which, by expanding the date range inputted into our visualization function, a high-quality median image is generated that almost always contains very few clouds. In addition, flood regions can be predicted even if clouds cover the view because we have that elevation data from SRTM. So now let's talk about our reflections. Let's start with challenges. There are definitely quite a few bumps along the way. For me, this was my first time using Google Earth Engine, so there's definitely a high learning curve to what I was working on. While working on the app, I ran into error after error, whether it be confusing Earth Engine objects with regular objects on the client side, or mixing up what input belonged to which function. But it's in these times like this that the power of a team really shines. My group was always there to help me out, and 9 times out of 10, we would eventually solve the problem.
For me, a coding novice, the most challenging part of our program was actually writing the code. We began the internship learning Python and Google Colab until we finally planned to use Google Earth Engine, which used JavaScript. Though this language was brand new, I managed with my team's and mentors' help. Additionally, when analyzing an image, I would have to limit the region of interest in order for the image to display in a reasonable time, limiting how far I can analyze an image.
I'm also not very familiar with coding as well, which means the beginning was kind of slow for me, and it took me a while to get used to these new languages that I was using. Eventually I got the hang of it for what I at least needed to do with the project, and moving from Python to JavaScript was a little bit confusing for me, but eventually I got the hang of it. Although I need to learn a lot more, I think this is a really good start for me overall.
For me, the most challenging aspect of this project was that to implement my algorithm, I needed to go pixel by pixel through an image and modify individual pixels, which unfortunately isn't how Google Earth Engine is designed to be used. I spent many long hours reading through the documentation, through Stack Overflow, and trying out different ideas. In the end, thanks to the help of my teammates and mentor, I did figure out how to do this using Python imaging library and the GEE reducers.
One of the challenges I experienced was figuring out the best way to convert the algorithm to something a user could use. The goal was to maintain ease of use. Initially, I was planning to develop a full web app using Python, which would contact Google Earth Engine through the REST API. Fortunately, Google Earth Engine had their own method to package up a project from the JavaScript code editor, and we were easily able to develop a user application.
So here are some of our best features and moments. For me, we were originally planning to write our web app like Aryan was talking about in Python and learn a new API to implement it, which would probably have taken a while. So I was super happy when we figured out that Google Earth Engine had a built-in functionality for publishing apps that connects directly with Google Cloud. And because of this advantage, our app is now out there for others to see and use this resource. It's extremely satisfying to know this.
The best feature of this internship was having the time and people to code with. For me, coding is something challenging to do alone, even with the internet. So having people to work it out with me was both more fun and informative than doing it all alone. A funny moment during my programming was spending 30 minutes finding an error in my code, only realizing that I forgot to change my checkbox's numbers.
The big thing I worked on in this project was finding a good set of bands to use, and I'll be the first to admit that after a while, it got kind of tiring and frustrating going through set after set after set. And when I finally found my golden bands, it was a huge relief and a great sense of accomplishment for me that I finally found this after I think it was 2 days of just straight looking.
For me, the best feature of SEAS is how we were given an opportunity to work on a relevant real-world problem and develop a solution that could actually be used. This is a very rare opportunity, as in most other high school programs, you only get a chance to work on the boiled-down versions of the problem. It's extremely rewarding to be working with real data, solving an impactful, meaningful issue.
For me, the best moment was when we beat that initial learning curve for Google Earth Engine and built a working algorithm, and also when all the elements came together and we were close to completing our project from what was just an idea a few weeks ago.
So, to wrap it up, you may be wondering how the SEAS program impacted us overall. Me personally, I feel very fortunate to have the opportunity to participate in something like SEAS. I mean, most high school students don't get to work with professionals on analyzing natural disasters, Zoom call with scientists and astronauts, collaborate with talented, like-minded peers, or present to such an awesome group of experts, parents, and students like our audience today. Although COVID-19 has caused an unexpected change of plans, it has also made this year's SEAS program incredibly unique, even expanding this amazing opportunity to a new group of students in our COVID-19 team. Anyways, my point is, SEAS is a one-of-a-kind program, and I will always remember my experience here.
Through SEAS, I've been able to create a project of my own with a team of talented individuals on a global issue, storm severity from climate change. Though only solving a portion of this global issue, this project on flood detection has provided a stepping stone in my path as an environmental engineer. Here, not only have I obtained valuable insight from talented individuals and educators across the states, but I also have access to a vast source of data and satellite images from large organizations like NASA and the U.S. Geological Survey. From this, I will use the knowledge and skills I attained in this program to work hands-on with engineers in solving this global change. Ultimately, I hope to create life-saving technologies to help communities, especially low-resource ones.
I've never really gotten an opportunity like SEAS in my school. My school doesn't really do anything STEM related, so working on a SEAS project has confirmed my want into going into the computer science field. It's also given me insight on what working with a good and efficient team can look like. And even though this whole thing was virtual, I think it's been a very good experience for me overall and will help me in the future.
SEAS has showed me how I can apply my software skills to make a real impact in the world. Through this project, I learned that I can already begin to tackle real-world problems with my existing knowledge. I am now inspired to continue to look for ways where I can use programming as well as other skills to truly make an impact and difference. I am more motivated than ever to continue my journey into computer science and entrepreneurship.
SEAS helped me learn about working with a team to develop software. I learned many new technologies for data analysis, which is a career path I'd like to follow. I also learned about how to solve problems and debug code. Overall, NASA SEAS was an amazing experience for me, and it's something that I will always remember.
So, I guess all that's left to say is
Thank you.
And as a team, we would like to thank NASA, the Texas Space Grant Consortium, and the University of Texas at Austin Center for Space Research for giving us the wonderful opportunity to participate in the SEAS internship program. We especially would like to thank our mentor, Ms. Howard, who has guided us on this project every step of the way. Again, thank you.